What's going on, guys? Justin here, and welcome back to our 19th example video following our course on proofwriting. Now, today's examples are going to be on composition, image, and pre-image. So let's go ahead and get into this first example. So this first example is just going to be a simple example of composition. We're going to define two functions f and g, which go from z12 to z12, and they're given by f of x is congruent to 7x plus 2 mod 12, and g of x is congruent to 5x minus 2 mod 12. And we want to find g composed with f. Now, like I said, we're just going to be using the definition of composition here. So we want to find g of f of x. And what this means is we will plug in f of x for our value of x in g of x. So we'll be making the substitution 7x plus 2 in for our x there for g of x. So g of f of x will be the following. We will have 5 times our f of x, like I said, which is 7x plus 2. And then we'll pick up our minus 2 from our g of x, and this will still be mod 12. So what's 5 times 7? 35. Plus 5 times 2, which is 10, minus 2 is 8. So we'll have 35x plus 8 mod 12. So g of f is congruent to 35x plus 8 mod 12. Great, so let's go ahead and get into another example. So for this example, we have two functions to find from R to R, f and g, where f of x is this piecewise function where f of x is 3x plus 1 if x is less than 0, and f of x is 2x plus 5 if x is greater than or equal to 0. And then we have g of x defined as 5x minus 7 for all x. We want to find, once again, g of f. Now, because this is a piecewise function, we're going to have to split it up into two cases, one where x is less than 0 and one where x is greater than or equal to 0. So let's go ahead and do the one where x is less than 0 first. So when x is less than 0, f of x is equal to 3x plus 1, which means we can evaluate g of f in the following way. We'll have 5 times 3x plus 1 minus 7. And that will give us, well, 5 times 3x is 15x. Then we'll have plus 5 minus 7, so then we'll have minus 2. So that is our g composed with f when x is less than 0. So next, let's do when x is greater than or equal to 0. So when x is greater than or equal to 0, we have the following evaluation for f of x. We have f of x is equal to 2x plus 5. And once again, we want to find g composed with f. Well, that's going to be 5 times 2x plus 5, and then we'll have that minus 7 at the end again. Well, what's that going to equal? Well, we'll have 10x from 5 times 2x, and then we'll have a 25 minus 7, which will give us an 18 here at the end. So we can put these two pieces together to write out our definition for g composed with f in a piecewise fashion. So g composed with f will equal 15x minus 2 when x is less than 0, and it will equal 10x plus 18 when x is greater than or equal to 0. And that is our final g composed with f. Great, so let's go ahead and get into another example. So this one says verify that f and g, which are defined from R to R, in the following way. F of x is a piecewise function defined as 11 minus 2x when x is strictly less than 4, and it's defined as 15 minus 3x if x is greater than or equal to 4. And then for g of x, we have g of x is equal to 1/3 times the quantity 15 minus x if x is less than or equal to 3, and it's equal to 1/2 times the quantity 11 minus x if x is greater than 3. And we want to show that f and g are inverses of each other or prove that they are not. So to begin, let me go ahead and write out our definition of inverse functions here so that we can use it to prove or disprove that these are inverses. All right, so there we go. I've written out our definition for inverse functions. So given a bijective function f from a to b, we say a function g from b to a is its inverse if g composed with f is the identity. We're using that notation from the lecture video corresponding to this example video, the identity of the domain, and f composed with g is the identity of our codomain. So basically what we're going to do is check that if we compose G with F and F with G, we get the identity in all cases, and if we do, we will know that they are inverses. And since these are piecewise functions, we have a lot to check. So let's start with f of x at the top there. Let's check the case where x is strictly less than 4, and then for g of x, we'll take the case where x is strictly bigger than 3. So when x is between 3 and 4. So let's consider x, which is strictly between 3 and 4. And we're going to look at g composed with f. So under these circumstances, g of x will be 1/2 times 11 minus x, and f of x will be 11 minus 2x. So that means that g composed with f is going to be 1/2 times 11 minus our f of x, which is 11 minus 2x. And we can see that these two 11s will cancel out, and that this negative here will make this 2x a positive, and this 2 will cancel with this 1/2, which will leave us with just x. So we can see that that is in fact the identity function, as if we plug in any x into g composed with f, when x is between 3 and 4, we will get x. So it will return the same value, which is our definition of the identity function. So next, let's go ahead and look at the case where x is less than or equal to 3 to get all of the smaller cases than this range we just established here. So we're going to consider when x is less than or equal to 3. And once again, we are going to look at g composed with f. So when x is less than or equal to 3, g of x will be equal to 1/3 times 15 minus x, and f of x will be equal to 11 minus 2x. So now we can go ahead and find our g composed with f. So g composed with f will be 1/3 times 15 minus our f of x, which is 11 minus 2x. And so that 11 will take our 15 down to a 4, and then we will be left with plus 2x. So this is equal to 1/3 times 4 plus 2x. And we can see that that is no good, as this will not give us an x, which means we do not have the identity when we compose g with f, in this case with x less than or equal to 3. But that means our function fails our definition for an inverse, and that these two functions are not inverses of each other. Great. So that completes our disproof of these two being inverses. So let's go ahead and get into our next problem. So for this one, we're going to define a function f from the natural numbers to the integers by the following. We will have f of n is equal to -1 to the n times 2n minus 1 plus 1 all over 4. And we want to find the inverse. Now we're going to do this using our standard high school way to find an inverse. We are going to set f of n equal to, let's just say, y, which is of course equal to our function -1 to the n times 2n minus 1 plus 1 all over 4. And then we are going to swap our y's and our n's and solve for y. So let's go ahead and do that now. So that will give us n is equal to -1 to the y times 2y minus 1 plus 1 all over 4. Great. So let's go ahead and start manipulating that by clearing the denominator. So we will have 4n is equal to -1 to the y times 2y minus 1 plus 1. Then we can subtract that 1 over, and we will get 4n minus 1 is equal to -1 to the y times 2y minus 1. Next, we are going to divide by this -1 to the y, but if you divide by any power of -1, it's the same as multiplying by any power of -1. So we'll just go ahead and write that in the numerator just for simplicity's sake. So once we multiply by -1 to the y, we will get 2y minus 1 is equal to -1 to the y times 4n minus 1. I just switched the sides there as we are trying to solve for y. Now we can add our 1 over. We will have 2y is equal to -1 to the y times 4n minus 1 plus 1. And lastly, we can divide by 2. So that will give us y is equal to, let's go ahead and split this up in the following way, where we have -1 to the y over 2 times our 4n minus 1, and then at the very end we will just have a plus 1/2 there. Now from here we can split this up into two cases depending on the power of our -1, whether this will be a -1/2 or a positive 1/2. So let me go ahead and write that out explicitly. So we have two cases. The first will be when y is odd. And when y is odd, we can evaluate that -1 to the y as a -1. And once we simplify, we will get that y is equal to 1 minus 2n. And then for our second case, we'll have when y is even, which means we will evaluate that -1 to the y as a 1 over 2. And when we do that, we will just get y is equal to 2n. So that means we have the following definition for our inverse function here, f inverse of n. Which we can define piecewise like this, where f inverse is evaluated as 1 minus 2n for odd n, and it's evaluated as 2n for even n. So there we have our definition for f inverse as we wanted. So let's go ahead and get into our last problem, which is a big proof. So for this proof, we have two if and only if statements, which means we need to prove the forward and reverse directions on both of these, which will give us a total of 4 proofs. So let me go ahead and read the statements. So we're going to suppose that f is a function from a to b, and we have x is a subset of a and y is a subset of b. So from here, I'm going to be using the terminology of image and preimage, as we have learned from lecture video 19 in this series. So we want to show that x is equal to the preimage of the image of x, if and only if f is injective, and that the image of the preimage of y is equal to y if and only if f is surjective. So let's start by proving our first statement first. And we're going to do the forward direction first. So we're going to start with the assumption that x is equal to the preimage of the image of x, and we want to get to the point where f is proved to be injective. And then we'll do the reverse proof, where we start with the assumption that f is injective and get to the point where x is equal to the preimage of the image of x. So like I said, let's begin by supposing that the preimage of the image of our big X is equal to x. And this will be for all x, which is a subset of A. And because we want to prove injectivity, we will go ahead and add on our setup for that as well. And so in addition to that, we will have A and B, which are in our domain A, such that f of A is equal to f of B. And recall from our proofs of injectivity, we want to show that that implies A is equal to B, and that will prove injectivity here. From here, we are going to define the following two subsets of A. We're going to let x sub 1 be just the singleton A, and we're going to let x sub 2 be just the singleton B. And we want to observe the following: that the image of x1 is going to be equal to the set of f acting on A, as x1 is just the singleton A. And by the same logic, the image of x2 is going to be equal to the set of f acting on B. But if you recall from our definition up here, f of A is equal to f of B, which means that f of x1 is equal to f of x2. But from our definition of the preimage of the image of x up here, that means we can write our singleton A in the following way. We have A is equal to x1, which is equal to the preimage of the image of x1, which from our equation above we know will be equal to the preimage of the image of x2, which is of course equal to x2 by our assumption up here. And then that will be equal to the singleton B. But that means if we look at our extreme left-hand and right-hand sides, we have A equals B. But that's exactly what we wanted to prove that this function was injective, as we started with f of A is equal to f of B, and we ended up with A is equal to B. So now let's go ahead and do the reverse proof. And so for the reverse proof, we want to start with the assumption that f is injective and show that x is equal to the preimage of the image of x. And since we have to show a set equality here, that means we have to do this by double inclusion. So we're going to begin by supposing f is injective. So suppose f is injective. And first we are going to show the forward inclusion. So first we're going to show that x is a subset of the preimage of the image of x. So we're going to do that by the following. We're going to suppose that we have some element A, which is in x. So, and then we are going to consider f of A, which will be in f of x. Now we can take the preimage of both of these, and we will get that A is in the preimage of f of x. But that's what we wanted to show. We wanted to show that we could take an arbitrary element from X and show that it was in the pre-image of the image of X, which is what we did. Great, so that completes our forward inclusion there. So let's do the reverse inclusion. So next we will be doing that the pre-image of the image of X is a subset of X. And since we didn't use injectivity for our first inclusion, we must use injectivity for our second inclusion. So just like before, we're going to suppose that we have an arbitrary element A, which is from our pre-image of the image of X. And we want to show that that means that A is in X. And so here is where we're going to use injectivity. So that means that there exists an f of B, which is in f of X, such that we have f of B is equal to f of A. But we know, since this function is injective, that that immediately implies that A is equal to B. But we know that B is in X, which means that we have proved that A is in X. And what did we start with? We started with an arbitrary element from the pre-image of the image of X, and we ended with A in X. So we've proved both inclusions there, and we've proved this set equality. Great, so that finishes our first proof here. So let's go ahead and get into our second proof. And for our second proof, we will begin with the forward direction as well. So we want to suppose that the image of the pre-image of Y is equal to Y for all Y, which is a subset of B. And we want to show that this proves that the function is surjective. So we're going to take an arbitrary element of our codomain B, which we'll call little b, and we want to show that there exists an A in A such that f of little a is equal to B. That would prove surjectivity. So now we want to consider the following set. We want to consider the singleton B, which is of course a subset of B, as we have just defined little b to be in B. From our assumption, that means that the image of the pre-image of our singleton B will be, of course, equal to B. Now we're going to do a proof by contradiction to show that the inside of our image there, our pre-image of our singleton B, is non-empty, and then we can finish this proof off. So by way of contradiction, we're going to suppose that it is empty and arrive at a contradiction. So we're going to suppose that the pre-image of our singleton B here is equal to the empty set. So now we're going to break that down a little bit. That means that the image of the pre-image of our singleton B here is defined in the following way. We have f of x such that x is in the pre-image of our singleton B will be the definition of our image of that pre-image there. But now we can use our definition of this being equal to the empty set. That means that we have f of x such that x is in the empty set, because we've defined this pre-image of the singleton B to be the empty set, which is of course equal to the empty set. But that's a contradiction, as we know from our original assumption that the image of the pre-image of our singleton B must be equal to B. So we've arrived at a contradiction. So that means that our pre-image of our singleton B is non-empty. And if it's non-empty, then that means that there exists an A which is in the pre-image of our singleton B here, which is defined in the following way. We have x in A such that f of x is in our singleton B. But just breaking that down by definition, that will give us that f of A is equal to B. But since we started with an arbitrary element from our codomain and showed that we could map an element from our domain to it, we have completed our proof of surjectivity here. Great. So now let's go ahead and do our reverse proof, which we are also going to have to do by double inclusion like we did for the last one. And at some point, we're going to have to use surjectivity in that proof. So for the reverse proof, let's go ahead and start with our forward inclusion here. So let's suppose that we have a function f from A to B, which is surjective. And now we want to show our forward inclusion. We want to show that y is a subset of our image of our pre-image of y. So we're going to start by taking an arbitrary element from y. So we're going to suppose we have b, which is in y. I'm using b instead of a here because y is a subset of our codomain capital B. So then we're going to consider the pre-image of b, which is in the pre-image of y. But now we can take the image of those and we will see that that means that B is in the image of the pre-image of Y. But that's what we wanted to prove. We wanted to take an arbitrary element from Y and show that it was in the image of the pre-image of Y. Great, so now we can show our reverse inclusion. So next, we want to show that the image of the pre-image of Y is a subset of Y. And we're going to have to do this using our definition of surjectivity, as we did not do it for our first inclusion. So just like before, we are going to take an arbitrary element, which we will call B, from the image of our pre-image of Y. And we want to show that that must be an element of Y. And right away, we are going to use surjectivity. So then there must exist some element A, which is in the pre-image of Y, such that we have f of A is equal to B. But because A is in the pre-image of Y, we know f of A will be in Y. So thus we have that B is in Y, which completes our reverse inclusion. And since we've done both inclusion directions, we have proved that these two sets are equal, which completes our reverse proof for this if and only if statement. So that finishes this final proof for this example video off, and that's a good place to stop.